Hello everyone, welcome to another robotics session. Today we're going to talk about control theory and application of control in robotics. This first video I'm going to generally introduce you to the field of control theory, some of the key terms that we will use in the next videos, and just give you a brief introduction in what is control. Consider a system like here when we have certain inputs and some output. Control means that we want to control or manipulate the inputs of the system in order to get the desired output. That is the main goal of control theory and the whole field of control. How to play with the system inputs in order to get the desired output. There are quite a lot of examples. It goes beyond robotics, and you've already probably encountered different control systems. One example is like a thermostat for controlling temperature in your room or in your house. How does it work? You want the room temperature to be a certain value, let's say 25 degrees, and you set the thermostat to control it and stay at 25 degrees. And the thermostat will turn the heat on and off in order to get to the desired temperature that you want. So it's controlling the input, which is turning on the heat in order to get the desired output, which is the desired temperature. Examples in industry, in plants, there's a lot in chemical plants, for instance, how to combine different chemicals and heat them at what temperature in order to get the desired product. This is control. In robotics, how do you control the joint inputs? How do you play with the joint variables in order to get the desired end effector position? That is control, and that's what we're going to talk about in the next videos on the topic of robot control. First, let's classify controllers and what are different types of control. One way to look at a control system is based on open loop and closed loop view. A control system can be open loop. In a sense, it means that it has no sensory information. You have a mathematical model that you use that to get the desired output. I gave this example before. Consider a robot working on a manufacturing line wants to pick an object and place it somewhere else. We already have developed kinematic models for such a robot that gives us the end effector position as a function of the joint variables. Assume we know the position of the object, we use the model to find the joint variables that bring the robot here and then ask it to bring it there. This is open loop control. We're using no sensory information. Everything is known and we assume the robot model is perfect and we can get the estimate of robot end effector position using the model. Another way is using closed loop control. This is, some people when they mention control, they mean closed loop control, when the controller uses the sensory information. For instance, the robot wants to move here, but it doesn't get there because the model that we're using is not accurate. And then we use sensors, for instance, a camera, to see how far is the robot from the object. Based on this error, the controller will update the joint variables in order to get to that point. This is closed loop. When there is feedback involved, there is a sensor that can measure the error of the output and based on that redefine the inputs for the system. There's other ways to categorize controllers. One is Seesaw and MIMO. Single input, single output, or multiple input, multiple output. Consider the system that you have. For instance, the thermostat. The input for that is turning the heater on and off, and the output is the room temperature. This is a seesaw system. One input, one output. Single input, single output. Most systems have multiple inputs, like a robot. You have multiple joints that you need to change in order to get the end effector position. This would be a MIMO. Other way to look at them is look at control system is based on what is the input signal, if it's discrete or continuous. In robotics, we're usually dealing with continuous signal. The joint variables change throughout the time. But some systems could be discrete. Again, the thermostat. The input could be turning the heater on and off. It's a binary input. Then the control that we need to design is called a discrete controller. And it's similar if you're familiar with digital and analog concept. It's the same. A controller could be analog or digital. A digital controller usually looks at fixed time steps throughout the time, and an analog is a continuous time signal. Essentially, even if the robot has continuous inputs, the way we program it would be discrete, because in the computer everything would be digitalized. So even if we are using joint variables like this as an input, the way that the computer sees it is breaks it into small discrete parts. So potentially our controllers are discrete or digital. Another way to look at the controllers is looking at the output. What is the output? There are two different types of controllers. One called regulating controllers and one are tracking, depending on what the output is. If the output is supposed to be constant, like again the thermostat case, when you want to reach a constant temperature, this is called regulation. The goal of the controller is to reach a specific point for the output and stay there. This is called regulation. Sometimes the output is time varying. This is called a tracking problem. For instance, the figure below. You want the robot end effector, the output of your system, to move on a time varying trajectory like this. So it's not staying at one point. This is called a tracking controller. Generally, designing tracking controllers are more difficult than regulating controllers. Finally, before I end this session, I want to give you an introduction to lots of the topics in the field of control. Control theory is a big field of research. There are so many different aspects in it, and we're not going to go into details, and we're mostly going to work with a simple type of linear controller. It's called PID controller, and it's used for systems that are, the equations for them are linear. There are different types of controllers beyond linear controllers. For instance, nonlinear controllers, controllers that are used for systems that are highly nonlinear. The equations are not linear. Optimal control. The goal of controller, as I said, is either regulate a signal or track for a robot to go and stay somewhere or move on a trajectory. Regulation and tracking. But sometimes you want to have certain performance. For instance, not just do tracking, but do it as fast as you can, or using least amount of energy. This would fall into the topic of optimal control. There are adaptive controllers. Adaptive controllers, as you can see from its name, can tune themselves and adapt themselves to the environment. For instance, a robot needs to carry an object with a specific size and weight. You design a controller to do that. But what if the size of the object or weight of it changes? The task is slightly different. How do you deal with that? This is the type of adaptive control that can adapt to changes in the desired output. Robust control. Robust control are controllers that are, as it says, robust against noise and disturbance. Example, for instance, you have a robot that needs to carry an object outside in a rough environment where there is rain and there is wind. You design a controller to do this task, move an object from one point to another, but suddenly the wind changes and there are forces pushing the robot away, or rain coming down, changing the weight of the robot links. A robust controller deals with these disturbances. If suddenly something is changing, there is source of noise or disturbance. Another one is stochastic controllers, controllers that deal with probability. when, for instance, the model of the robot is really not fully determined. There might be a sudden change based on a specific probability. There are intelligent controllers where you use artificial intelligence to control the input and get the desired output, and also chaos controllers when we're dealing with a system that's very, very nonlinear and has a semi-unpredictable behavior. So these are the topics that different controllers that exist, and we're not going to go through these. They will take 4 or 5 courses to get familiar with all these types of controllers. We're going to stick with a simple type of linear controller and use it to control motion of the robots. And in the next video we talk about this controller.